Hello guys, so today what I want to talk about is really artificial intelligence, and one of the very crucial really aspects of artificial intelligence, which is at the heart of, let's say, the large language processing or the large language models which have come out, right? Gemini, Claude, DeepSeek, you name it, right? And Chat GPTs, etc. All the GPT-1, GPT-2, 2, 3, 4, etc. All those models basically rely on something called as transformers, and transformers are at the core of generative AI basically. So what is transformer? Basically, transformer transforms the context of the user to the trained learnings which the models have undergone already, so that it could do certain tasks. It could do certain predictions. It could do contextual language generation. In the language generation task, could do something, some kind of task fulfillment, in task fulfillment kind of task. So there are various type of transformers which are supported by various kind of models which are there currently. And if you see the architecture of transformers, right, the user really goes ahead and provides a prompt to the large language model, and there is where the transformers kick in basically. So you have the tokenization, where you divide the prompt into multiple words and assign them certain kind of tokens, or nothing but the token IDs, and then you have so this is the basic layer of tokenization. And if you see, the prompt is the cat sat on the mat. So here you would generate 6 tokens based on the 6 words which are provided, and each word would be splitted based on certain tokenization methodologies like character splitting, sequence splitting, word splitting, etc. So imagine, for simplicity, there is 6 tokens which are generated out here. Those in this tokenization process would be assigned certain token IDs, and now you have the token IDs representing each 6 words here. So the next step which really occurs is the embedding layer, and the embedding layer and the positional encoding. Here is where you will be assigning each token ID certain set of vectors, and those vectors may be stored on the vector DBs, which will be part of the LLMs basically. So here you will be generating some kind of contextual information for the LLMs to really understand what is going on. So they might not really know actually the user input, right? But once you provide them with certain set of vectors which are already stored as part of their learning methodologies, now they have a context on which they can do some kind of task, match and do a semantic search, and really assign some kind of cosine similarities, etc., and generate some kind of outputs, basically the natural language processing part of your LLMs. So here you will be getting your vectors, and those vectors could be existing across multiple dimensions based on the power of your models being used. It could be hundred of dimensions. So one uh, token, for example, cat could be converted into, let's say, an array of numbers, and there could be 100 numbers in that array. So that single representation would be your cat in the form of vectors. Now if you have 100, it's basically 100 dimensions. So that means your LLMs are, your models are very powerful. For simplicity, we'll assume, let's say, it has 3 dimensions. So each of the token which is generated is converted into an array of 3 numbers each. So basically 1, 2, 3. Then cat would be something like 3, 4, 5. Sat would be something like I don't know, name some number. So it would be that, right? So but now you have the semantic information, but you don't have the syntactic information. To provide that, you basically do something called as position encoding, so that your LLM knows at which word comes before which word, and what is the sequence of the prompts which is maintained. So one set of vectors which are generated, one set of embeddings which are generated, will be placed next to one set of embeddings in the order of the basically the prompts which are being generated, which the tokens which are generated. So now you have the positional information. So this positional encoding information is fed into the vector representation, so that you know which token comes before which token, which vector comes before which vector, so that the semantic and syntactic both informations are now preserved. And now you can pass your information to the transformation layer. At the transformation layer, basically it's the heart of the LLMs, where you will be dealing with something called as attention. So if you would have read the papers on attention, you would know that attention is nothing but creating relationship between the various tokens. So only if there is a relationship between different tokens, you the LLM will know that okay, this has to be the context which has to be generated, and there is a semantic or there is a semantic matching, there is a semantic search which has to happen in this sequence, because the meaning is derived from the attention part of it, right? So that is how your suited context could be generated, suited knowledge could be generated, and suited task or targeted task could be accomplished in the targeting manner as you want it, right? So what is attention? Basically, you have certain kind of token representations over your, let's say, three-dimensional layer which we are discussing right now. The cat sat on the mat has the first token as D, so it could be represented by 1 2 3. So now 1 2 3 basically needs to be established a relationship with cat. So and sat and on and the and mat, so that part is done using attention. So you get a weighted average, you get a weighted notification, a vector representation of the in relationship to all the other tokens which are existing on that user input, so that now you basically can derive the attention, derive the relationship between each token when compared to every other token. And this process is repeated for cat, sat, on the, and you get the idea, right? Basically it's repeated for all the tokens and you get a weighted average in comparison to every other token. And this is done through something called as dot products, and you apply a, a search, basically you create three kind of important vectors, just query key and values. And based on query key values, you the generated query key values, it could be linear transformation, so the query key and value could be same as the vector embeddings which you are generating. You apply certain softmax functions on top of the query key and value, and then you do a dot product of the values so that you get a final representation of your each token. So in case of 3D, it will be again a three dimensional representation of each token. So 1 2 3, for example, for D could be converted to 3 4 5 at this step. And then you have your adding a normalization layer, where you would be providing the context from the user input to the output which is generated by the self attention layer. So these are called as the residual connections. So the input is provided to the output of the attention layer, so that a semantic information is generated or contextual information is generated with respect to the let's say the input which was provided. So now your LLM has a better understanding once it derives the weight of each token with the other token, as well as it has the input normalization which is done. And then this final representation could be fed to a complex deeply connected layer which is called as a feed forward network to do further processing, such that it adds more contextual information. The output is what you really expect to be generated, right? And this is called as the let's say the layer, the iterative layer. Okay, so this could be your first layer, and there could be, like, let's say 6 7 layers, or there could be n number of layers based on the power of your large language models which are being used. And you would have a vector representation generated after each iteration for each token, based on the different layers of transformations which are applied. So let's say at layer 1, the cat sat on the mat. Cat was converted to 5 6 and 7 after your layer 1 iteration from the feed forward network. That was your output representation. And then again the same process repeated 6 times. You went through the multi-head attention, you went through adding a normalization, then you again went through feed forward network 6 times, and let's say the number was converted now to 10 11 12. So adding more contextual information. So as many times you iterate, you establish better relationship between your tokens which are existing in your prompt. So now you have better similarities, better semantics, better syntactics which are associated with the vector representations which are generated at, let's say, layer 6 and layer 7 than it was at layer 1. So what this does is it helps the LLM to do predictive analysis, right? So now your predictions will be more stronger, and it will be consistent with what you are really expecting, because the LLMs are also trained on certain set of data which are also stored as vectors. So now it could really compute the relationship between the vectors which are provided and the vectors on which it is trained, and establish a better output based on the trained data set, right? So now it could generate a better output for your input context. So your input could be the cat sat on the mat and generate the next sentence. So it could generate something, then it got out of the mat. So for example, this is done how this can only be done if you have the contextual information about your input, so which is matching or which is consistent with the data on which it is trained. So only if you have the computers understand numbers, right? So only if you have this vector representations, apple compared to apple, you could generate a context out of that, which will be consistent with what you want or what you are expecting, right? So this is how predictive analysis, this is how decoding is done. So there are different kind of tasks based on the different type of transformers you are using. It could be encoding task, it could be decoding task, it could be a combination of both, it could be predictive tasks. So based on what you really want, you can achieve that because you have this transformation layer which is existing. So this is what I was talking about. The cat sat on the mat, and the cat is converted into 6 tokens here, and each token then uh, after the tokenization process goes through the embedding layers where you have the vector representations generated, and you can see the vectors are juxtaposed or they are stored next to each other, providing the position encoding information. And then you have the transformation layers where you compute the attentions, you compute the similarities, you apply the softmax functions, and those functions basically do some dot products and compute those dot products at weighted averages, and you have some final representations, right? So for example, at layer 1 it could be 0.5, 46, 4.57, right? This is just an example. So and this layer of transformation could be repeated n number of times, and really the final output could be something else with a deeper contextual information, deeper relationship between the different tokens, and deeper relationship between the data set on which it is trained, so that your task could be achieved, task could be fulfilled as per your expectations, and not just on the hallucinations which are part of LLMs. So this is how you really hammer in the advantages of using this kind of architecture, and this is how you really go for creating more contextual based information. So more when you're providing more transformations to the layers of inputs which you are providing, such that the LLM is able to achieve the intended task, and the LLM gets the idea about what you are expecting based on the input which you are providing. So LLMs are basically these transformation layers plus the trained data, right? If you take transformation data out of your LLMs, there is no LLMs, because it just has the information about the context on which it is trained, but there is no transformation which maps your input context to the let's say the context which is stored, or the context on which the LLM is being trained. So this transformation has to happen between your input and the stored context to finally generate an output from the LLM or do a certain task from the LLM. So this is the importance of LLM. And if you take out LLMs, if you take out transformers, this is the importance of transformers. If you take out transformers from LLMs, there will be no natural language processing. So this is how you achieve the various models are basically in the market, and this is how they are achieving this natural language processing, the task associated with your user inputs. You can name the task, you know about it, right? You would have the experience, but this is really the foundational stone of generative AI. And if you really want to go towards generative AI, your foundation on transformer should be really strong, and you should really understand these aspects. There are many moving aspects in AI, but this is at the core of large language models. So this is what I wanted to talk about today, and I'm quite happy to be talking about this topic, because really this is the buzzword in the industry, and I will be coming up with more such videos in the near future. So stay tuned, guys, and thanks for listening to me. Thank you.